Today we discuss elementary properties of a group. First theorem, cancellation law. If G is a group with a binary operation star, then the left and the right cancellation holds in group G. For all AB element in G, A star B is equal to A star C. That implies A is equal to B is equal to C. That is, cancel out A from the left and we got B is equal to C. Similarly, B star A is equal to C star A. Cancel out A from the right and B is equal to C. That is cancellation law. For example, A, B, C are invertible matrices of the same order. Then we know that the set of all invertible matrices of same order where the operation matrix multiplication is a group. Here matrix AB equals CB. Then we can cancel out B from the right and that implies A is equal to C. Next theorem, uniqueness of identity. In a group G with a binary operation star, there is only one identity element E such that E star X equal to X star E equal to X. That is, in a group where exists an identity element, that identity element is unique. Okay. We couldn't find another identity element. For example, if the identity element is E, suppose there is another identity element E1, then E1 star X equals X star E1 equals X. Okay. Also, X is equal to X star E because E is also an identity element. So, X star E is equal to X and the X star E1 is equal to X. So, from this we get X star E1 is equal to X star E. Cancel out X from the left, we get E1 equal to E. Identity elements are equal. So, a group has only one identity element, a unique identity element. Next, uniqueness of inverse. Uniqueness of inverse. In a group G with a binary operation star, for each A element in G, there is one and only one inverse element, A inverse, such that A inverse star A is equal to identity, where identity element is in G with respect to the operation star. That is, for every element in a group G, there exists a unique inverse. If A is an element in the group G, then A inverse exists. That A inverse is unique. Okay. For each element, the uniqueness of inverse means for each element in the group G has an inverse. Okay. And that inverse is unique. But for the uniqueness of identity elements means the group has only one identity element. The group has only one identity element. Okay. Next theorem, a reversal law. Let G be a group. Let G be a group. Reversal law. Let G be a group. For all AB element in G, we have A star B whole inverse equals B inverse star A inverse. Okay. In the group G, A star B whole inverse is calculated by B inverse star A inverse, not A inverse star B inverse in case of a group. But if a group is abelian, then B inverse star A inverse equal to A inverse star B inverse. That is, if a group holds the commutative property, that means G is abelian, then A star B whole inverse equals A inverse star B inverse. Otherwise, A star B whole inverse not equal to A inverse star B inverse. In a non-commutative group, A star B whole inverse is equal to B inverse star A inverse only. Next theorem, let G be a group. if the inverse of A is A inverse, the inverse of A inverse is A. Okay, you know that multiplicative inverse of 2 is 1 by 2. Then the multiplicative inverse of 1 by 2 is 2. So if A is the inverse, sorry, A inverse is the inverse of A, then definitely A is the inverse of A inverse. Now we discuss a problem. If star is a binary operation on a set S, okay, star is a binary operation on a set S, an element x of S is an idempotent element if x star x is equal to x. That is, x is idempotent means x star x. X operate with itself, then we get x. Then that element is idempotent. Prove G has exactly one idempotent element. Prove that G has exactly one idempotent element. Okay. If G is a group, then G has only one idempotent element. Okay. Clearly, E is an idempotent element. Clearly, E is an idempotent element. E is an identity element in the group G. Then definitely E is an identity element in the group G. Then E star E is equal to E. Identity star identity is equal to E. So therefore, clearly E is an idempotent element. Clearly E is idempotent. Let X is another idempotent. X is another idempotent. Let X be another idempotent. G is a group, therefore X inverse exists and X inverse belongs to G. Then identity element E is equal to X star X inverse. That is equal to X is an idempotent element and therefore it is X star X inverse. We can write X as X star X. That is equal to, by associative property, X star X inverse. That is equal to, what is X star X inverse? X star X inverse is identity element. That is equal to X. So we get identity element equal to X. Identity element is an idempotent element in the group G, and that we let X be another idempotent element, and we prove that identity element and idempotent elements are same. So in a group G we have exactly one idempotent element, that is the identity element. Okay. Next problem. If AB whole square equals A square B square, then show that the group is abelian. Okay, we have AB whole square equals A square B square. We know that AB whole square is AB into AB equals A into A square into B square. By associative law, we can write it as A into BA into B equals, here also use associative law, A into AB into B. Okay, here we use associative law. By left cancellation, we cancel out A from the left. We get BA into B equals AB into B using left cancellation. Then using right cancellation, we cancel out B from the right by using right cancellation. We get BA is equal to AB. Cancel out B from the right, we get BA is equal to AB. Hence, the group is abelian. Okay, That is, if AB square equal to A square B square. If it is a non-abelian group, AB square is only AB into AB. Here it is abelian, then AB square is equal to A square into B square. Okay, A square, AB whole square is equal to A square into B square, then that group is abelian.